go. Okay, we're now recording. So you can see here, in case you guys probably forgot, these are box Whisker plots. Not sure if it really matters for our discussion today, but this right here would represent your max. The bar itself was called the IQR, or the interquartile range. Remember, quartiles are from the 25th to 75th percentile. So, for example, I know some of you guys are maybe considering taking the SAT if you're a junior, or maybe you did it last year. Maybe you didn't even do it, because law school's gone optional. But and I know many of you guys are also looking into colleges, or got into college and you're visiting colleges. When you look at like a college's interquartile range for their SAT scores, say for example, a school has an interquartile range of 1200 to 1300, then the 1200 would mean that if you scored 1200, that's better than 25% of the applicants. So 75% scored higher than you. Or if you say the upper end of that interquartile range is 1300, that means that your score of 1300 scored better than 75% of the people at the school, or 25% scored better than you. So it's just a kind of like a ranking, in case you guys forgot. And that's what's going on in this image here, but not sure if we'll really need that for this presentation. So we're going to talk about something called statistical inference. So when you infer something, it's really more like what you're concluding in a way, or kind of assumptions that you're making about your data. So it provides methods for drawing conclusions about a population from sample data. So let me emphasize this part right here: population and sample. So say, for example, last year around this time, you were curious to know how people in Menlo Park will vote in the presidential election, or let's say San Mateo County. We'll do San Mateo County. How would they vote in the presidential election? So the population would be the 700,000 people in San Mateo County, right? Now, would it be feasible to poll everyone in San Mateo County of voter age, or eligible to vote? So I don't know, maybe 60% of the 700,000 people are eligible. I don't know. I'm just throwing a number out there. But would it be feasible to still survey, 400,000 people or 500,000 people? How are they going to vote in the election? No, that would just take too long, right? It's just too much data. So instead, you want to do a sample. A sample is basically a much smaller group, but hopefully representative of the population. Okay. So what if I said, okay, well, I want my sample to be maybe 1,000 people. So it's kind of some review of sampling. So 1,000 people in my sample, which is probably doable. You could probably create a survey, send it out to people, or maybe stand in front of a Starbucks or something. I don't know. Of course, in the pandemic, that would have been a little hard, so you probably would have to do it online. Well, what if I just went door to door in the town of Atherton? I didn't really, I was being lazy and I'm just gonna kind of do it and just knock on the doors and say, hey, who are you voting for, Biden or Trump? Would you think that would be representative of the population of San Mateo County? Yes or no? You can put it in the chat, or you can speak in your microphone. Good. So Will and Aiden, you guys are saying no. So Will or Aiden, either one of you guys, why would you say no?
Because it's only one town in the entire county.
Yeah.
And it's also
and it's also, go ahead.
I was just gonna say there's a you might not get a fair representation.
It'll be biased, yes, good. You took the words out of my mouth. People in Athens are very, very wealthy. We'll just put it out there. People who tend to have wealth tend to probably vote for someone who's going to protect their wealth. Perhaps maybe they might vote for a candidate that is going to favor lower taxes, which is usually tends to be the Republican candidate. Just going to kind of throw it out there. But of course, there might be some people who didn't like Trump, or maybe some people didn't like both candidates. Maybe they were going to abstain from voting. But regardless, you're kind of just focusing on a lot of people are very similar. It's very homogenous, right? Well, okay, fine. What if I went to, say, down the street, I went to Middle Afton High School, and I just asked all the seniors there who are 18 years old, and then say I also went to Woodside High School, and I'll ask all the seniors there as well. So I'm going to 2 different schools, okay, Woodside and Middle Atherton, and asking all the seniors who are 18 or over, so I get about 1,000 people because those are big schools. Would that be representative of the population of San Mateo County? Yes or no? Yeah, I'm going to 2 different schools. You can put in the chat. What do you guys think? Again, it should be no, exactly, because I'm asking a bunch of people who are very young. Young people tend to be a little more idealistic. I think we'll probably get a little more diversity, perhaps, racial diversity, definitely for sure. I think socioeconomic diversity for sure, but maybe not. Maybe I don't know, because Woodside and they're still in pretty affluent areas, but yeah. So what I probably would want to do is I'd want to randomize. That's what you want. You're gonna want to randomize your sample. And there's different ways you could do that, and I think we kind of talked about a little bit last semester. I'll get into that down the road because I don't want to go off on tangents here. But yeah, like it would be good maybe, yes, survey some people at a high school, survey some people in Atherton, maybe go to downtown Menlo Park, maybe go to Sequoia Station, maybe go to Hillsdale Mall, maybe go to the park where I am right now. That way you get a more representative sample, but it should be randomized also. Like in the way sometimes you would randomize. Now I'll kind of talk about how you would randomize it. You'd have like the 400,000. Say you have a list of 400,000 people in San Mateo County who are voting age. You give them a number and use a random number generator. And then when you do the random number generator, maybe we'll spit out 1,000 numbers, and then from those 1,000 numbers, you use that to identify the people from your population that you'll actually survey. And so if you're one of the lucky 1,000 people that are selected, then you'll be asked. And so that way, you're kind of ensuring that you're getting a more representative sample when you randomize it. Of course, you'll look at the demographic data still. And if you realize, oh, shoot, like, maybe just by chance you happen to, get like a lot more Caucasian or a lot more people who are, very aware of wealthy, then maybe you do it over again because, you want something that would represent what San Mateo kind of looks like. So from that, when we do the survey, we do something called the confidence interval. Now, some of you guys might remember from the election, for example, let's see if I can actually look it up right now. 2020 presidential poll, let's say in September. Okay. So if you look over here, it said that Biden had a 52 to 42% lead over Trump around September of 2020. If you do the math, 52 plus 42 is 94. So where's that extra 6%? Where did that go? It seems kind of weird, right? Maybe those 6% might want to vote for someone else, right? Or maybe they don't want to vote in the election. Maybe they want to do a write-in candidate. But also you have to leave a little bit of room for error, and that's what a confidence interval is pretty much like. It's like estimating the error. So going back to this again, a confidence interval takes into account any error for your data. Now, as you guys know, if you've studied civics, to win a presidential election, you do need at least 50% of the electoral college. Sometimes that doesn't go hand in hand with the popular vote, as we saw in 2016. Hillary Clinton won the popular vote, but still lost the election, right? And so, you know, it was still a very close election. I mean, yes, Biden did win. I mean, yes, it was contested. We don't need to get into all that stuff. But Biden had 52%. But I would argue that it was probably a plus or minus maybe 4% or so. So there was kind of that iffiness, like, well, maybe he didn't get 50% of the popular vote, and maybe that wouldn't get him 50% of the electoral college. And you could see why probably those who were Trump supporters probably were fighting so hard to contest the election, because it was very close. I mean, in fact, we had like 5 or 6 states that you know, Trump was leading on presidential night, and then it swung towards Biden when the mail-in ballots were counted. So yeah, I mean, you know, sometimes, you know, we are a little iffy on that. And so, you know, if Biden had 60% with a plus minus 4%, then you're like, you know what, he won. You know, let's, you know, not really kind of challenges here. But, you know, we do have to sometimes generate a confidence interval to kind of provide a fair estimate of what we expect to happen. So like a range, basically. That's kind of what is happening here. First off, we have to estimate what his percent of votes you can get. That was 52%. So we call that our parameter, which is usually like a mean or an average. There are tests of significance. I'm not sure we're going to get to that. So I'll kind of just cross it off for now, because I might need more time to talk about that. I don't think we'll have that time. But let's move on to the next slide here. So SRS. SRS stands for Simple Random Sample. So we know what a sample is. It's a proportion of your population. Like if you have like 400,000 people in your county that can vote, you want to survey 1,000 of them. Random, you really want it to be represented. You don't want to just like say, oh, I'm just going to focus on one area. That's not random. That means you're deliberately being biased. And people are not going to really accept your results. In fact, they're going to question your ethics if you don't randomize it. So we want to be very ethical when we go about our data collection and analysis. And how do you randomize it again? You could probably assign a number for each person and then use a random number generator, or kind of think about like putting all the numbers in like a bin, or like one of those like lottery spinning machines, and you just draw the numbers out randomly. Obviously, using a computer is probably going to be the most effective way. There are a lot of random number generators you can find online, or people can just, you know, design their own code and use that. And then simple. You don't want to make it too complicated. If you can, keep it like again, what I just did, just give everyone a number, and just you can find and just draw 1,000 numbers from those 400,000 numbers. You do have to assume a normal distribution. So you know, we do have to kind of investigate our data and make sure, okay, is it following a normal distribution? Remember, normal distribution looks like this. We talked about it last semester. So this would be the mean, and also the median. The mean and median are going to be identical when you have a normal distribution. This we call actually the mean. It's a Greek alphabet. It's called mu. And then this right here is your standard deviation. We talked about standard deviation in the past. So STDEV. And we call that sigma. That's another Greek alphabet. We'll talk more about mean and standard deviation in a little while. And mu, just so you know, is a population mean. So it's mean for the whole population. So for example, if you were to say of all the people in San Mateo County, the 700,000 people, so forget about the election. Let's forget about that. Let's just focus on all 700,000 people in San Mateo County. I want to know, what is the mean age of people in San Mateo County? If I were to guess, probably in their 40s, I'm guessing, because there are some young people, there are babies in San Mateo County. There are really old people as well. But if I were to guess, probably the mean would be somewhere like maybe my age. I'm 43, so maybe something like that. But we really don't know, right? So if I want to actually estimate what the population mean, I would take a simple random sample. And of course, I still am not 100% sure about, or 100% confident. I'm using the word confident after talking about confidence intervals. I'm still not 100% confident if I do a sample that it's going to be the true mean, but it might be close enough. And that's why I have to do something called the confidence interval. But the standard deviation, we will assume is known. So we will assume that we do know the population standard deviations, which is sigma. So let's keep moving. Okay, so confidence interval for a parameter. So really it's just this right here. I don't know, I never really call it level C confidence interval. I'm never sure where that came from, but let me explain these two items here. So estimate plus margin of error. So the estimate would be your mean and the margin of error. So say, for example, I wanted the mean age of people in San Mateo County. So let's say it's like 43, but maybe I'm off by about 2 years or so. So I do 43 plus minus 2. Like maybe, the mean age is 41. Maybe it's 45. Maybe it's somewhere in between. So that's what a confidence interval is. It's a range of values. And then, we actually want to assign a level. So I guess I know what they meant by a level C confidence interval. We want to assign a level to the confidence interval. So how confident are you? Are you 90% confidence? Are you 95% confident? Are you 99% confident? Are you 99.9%? Are you 98% confidence? There are a lot of different levels of confidence you could have. And so it's basically how successful, it's kind of a rate of success with your interval. So for example, if you have a 90% confidence interval, and I'll abbreviate as CI for short because it gets kind of cumbersome to write confidence interval. If you have a 90% confidence interval, and say the 90% confidence interval for the mean of mean age of people in San Mateo County is 43 plus or minus 2, then I would say I'm about 90% confident that the mean age is from 41 to 45. And the lower the confidence, the wider the range. So the lower your CI level, so that way you could be a little bit more, actually I take it back. That was actually wrong what I just said. Well, let's come back to that in a little bit, because I don't think we're ready to have that discussion just yet. We'll come back to that part. Let's move on to the next page. Okay, so let's look over here. So Ben's data records the high school placement test scores. Remember that we used to do high school placement, we don't do it anymore now, for a particular class. Scores range from 71 to 140. We know the standard deviation is 10.195. So this is the lowest score. That's the highest score. You're curious to know, what is the range, what is an appropriate range for, or confidence interval for high school placement test scores for Sacred Heart? Okay. Now we usually have 150 kids in every incoming freshman class. And let's just say we sampled 20 of them. We didn't ask all 150. Now we could actually get a mean for all 150 because we have that data. But say for example, you sampled 20 and you found it was 112.4. Okay, fine. On the basis of sample, estimate the mean score of 153 applicants. So I'm going to show you how you're going to compute a confidence interval. Now, just so you know, X bar is the sample mean. So it's the mean of your sample, which we knew on the previous page was 112.4. So X bar is 112.4. And we know it's probably going to be pretty close to this because you're assuming that you did a random sample, right? But But how do we estimate how far off it is? Okay. Now, we do know the population standard deviation. That was, again, given to us on the 2 pages ago, 10.95. So we can estimate the deviation of the sample distribution from that. So SD is the standard deviation of your sample. And there's a formula that goes with it, and it's right here. There it is. Some people just use the letter S. They don't use the subscript D. It's up to you. But it's sigma, the population that is divided by the square root of n. N is your sample size. So in this case, you do 10.95 divided by root 20. And the reason why it's going to be smaller is because we are dealing with a smaller group, right? So you're not going to have, the data's not going to be as spread out as it would be for the whole population. So that's just a formula that a bunch of statisticians came together and figured, hey, this is a good estimate for the pot. And they kind of, I guess maybe through a lot of research and looking at like just lots of data from surveys from all walks of life, they probably figured that's probably a good formula to use. So sigma over root n is a sample standard deviation. Now, remember normal distributions from back in the day, from the fall. We did talk about, so we're doing a kind of a review of this. So, so our standard deviation is 2.45, right? Now remember, whenever you're within 1 standard deviation of the mean, let me use a different color. So whenever you're within 1 standard deviation, within plus or minus 1 standard deviation, that's going to represent the middle 68% of the data. So again, you know, if we don't know what the mean is, we'll call this, well, actually, for our sample, actually for the population, we'll call this mu. We don't know what that is, so mu. And this is sigma, and that's negative sigma. So mu plus or minus sigma will represent 68% of data. So say, for example, the population mean of the scores is 120. Actually, we'll go for the sample. We'll do it for the sample. 112.4 plus or minus 2.45. So anyone who scored maybe a 114.85, if I add 112 to 2.45, or if I subtract it, which would be, I think, 108.95, anywhere in that range would represent the 68% of our data, or so it should be that way. 95% would be within 2 standard deviations. 99.7% would be within 3 standard deviations. So you can see that when you do 99.7%, it's definitely a wider interval. It's going to be more encompassing. So you have more confidence. So actually, I told you guys false information about the wider the confidence interval, it's actually more inclusive. So actually, it's a higher percent of confidence. So the wider the range, the higher the level of the confidence, because you're more confident you're going to be within that range. When we have a very small range, you're not as confident. So you're like, okay, well, yeah, Joe Biden's going to get anywhere from 51.5 to 52.5% of the vote. Like, you're being pretty bold when you're saying that, but then your confidence level is going to be pretty low as a result. If you said, hey, I'm you know, Biden's going to get about 48 to 56% of the votes, that's a pretty wide range. You can say I'm 99% confident that's going to happen. So because it's a wider range. So that's what I meant to say about a few minutes ago. So I apologize for any confusion there. And we're going to talk about the width of the intervals and stuff like that in just a little bit. Okay, so let's keep moving here. Any questions so far, by the way? If you have any questions, please feel free to put in the chat or speak in your microphone. No? Okay. Let's keep moving. So now there are, I guess you could write these as error bars, perhaps. So in graphs, these confidence intervals are often set at 95%. So use 95% is kind of the typical. It's kind of a typical CI level, you know. So essentially what you're doing, like in this case here, let's say the mean, so I'm not sure what is being measured here, but if we take a look at, these are two different bars. Hold on a sec. I'm trying to understand what they're doing in the schematic. I mean, I guess if you just looked at like our high school placement test data, this stuff here just seems a little silly to me. But $112.4 and say you're doing a 95% CI or confidence interval. And remember, our standard deviation was 2.45. Then this part right here is going to be 112.4 plus 2.45. This part right here will be 112.4 minus 2.45. And so that's how you would draw it. So I guess the cartoon is off because it doesn't show that part, apparently. So, and we're not really sure what the mean is. So it just seems weird. Okay. Let's look at this data here. So strictly speaking, what is the best interpretation of a 95% confidence interval for the mean? Okay. So if we look at each of these example here, so if repeated samples were taken, the 95% confidence interval was computed for each sample. 95% intervals would contain the population mean. If you look at B, a 95% confidence interval has a 0.95 probability of containing the population mean. 95% of the population distribution is contained. Yeah, I wouldn't say 95% of that. I don't think C would really make too much sense there. That seems kind of weird to me. I think A probably would make the most sense. Because if you were to redo your sample over and over again, the whole point of this is that 95% of the intervals would actually contain the true mean of the population. So A probably seems to be making the most sense. The fact that you're repeating the samples, and you can see that here they do this at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So here we have obviously 25 intervals, different confidence intervals from 25 different samples, and one of them is out, whereas the other 24 are in. Well, 24 out of 25 is 0.96, or close enough to 95%. So yeah, it seems like if you were to repeat your study of high school placement test scores, so you do a sample survey, you ask 20 people what you got on the high school placement test, you calculate the confidence interval, awesome. What if you do that 24 more times? If you do a 95% confidence interval, of those 25 confidence intervals, one of them probably would not contain the true mean, the other 24 would. And that's what's meant by having a certain level of confidence, is that if you repeated the interval over and over and over again, how often would the interval actually contain the true population mean of what you're studying? So A seems to make the most sense here. B, kind of close. has 95. It's really nothing to do with probability, just so you know. It's not really, I mean, yes, we are looking at the probability of one of the intervals not containing the mean, and the others are, that would contain it, but it's not so much that the interval itself has 95% probability. It's just if you repeat it over and over again, how many of those intervals would actually capture the true mean. And then C makes no sense at all. It's not 95% of the population, just so you know. So that's just so far from the truth. And that's why I feel like it's important that we talk about this, because I don't want you leaving this class and someone asks what a constant is you don't know, or you get it wrong. You know, at the very least, I want to make sure that you, no pun intended, that you are confident to explain what a confidence interval is. So let's keep moving. So careful interpretation of confidence interval. We are 95% confidence at the mean. I don't know what NAEP stands for. Maybe some tests that people take. For the population of adult males between that. Okay. So those are possible results we can expect. So it does not mean that 9% of all males would score that. So you got to be very careful about that. For example, what if I did the mean age? Let's go back to age of San Mateo County, right? So let's say the mean age is 43, plus or minus 2, right? And say that was a 95% confidence interval. So does that mean that 95% of people in San Mateo County are between the ages of 41 to 45? No, that's not true at all. I mean, there are a lot, I mean, maybe 10% of the people in San Mateo County are at ages between 41 and 45. So you gotta be very careful about that. It doesn't mean that 95% of all the people are in that range. What it means is that if I were to repeat my study maybe 100 times, that of all the different confidence intervals I would compute, that 95 of them would actually capture the true mean of the population of the ages of San Mateo County residents. So that's really what it means. And so if you look over here, 9% of all samples of size, like if you survey 840 people, apparently this survey here, from the population of males should yield sampling within 2 standard errors of the population mean. And I guess the reason why I say 2 standard errors, I guess this is plus or minus 2 standard deviations for this one here. But anyway, so that's how you would interpret it, that 9% of all the confidence intervals would capture the true population mean. Now, how do you calculate the confidence interval? Let's talk about that. And one thing we'll probably do is I think we'll probably try to power through to about 1:30ish or so, and then I'll probably end class a little early for you guys. That way, you know, not burning out on Zoom calls, but we'll just kind of just kind of power through this, and then tomorrow we'll do some practice of this stuff, and I'll help you and I'll guide you guys through the process. So calculate confidence for the mean of a normal population. Okay, so you can calculate the score needed to reach any confidence interval. This compares your values to a standard critical value called Z. Now, you guys might remember Z scores. We did Z scores back in the day, where Z score was simply your sample minus your mean divided by sigma. And Z basically represented the number of standard deviations above or below the mean. Again, X is going to be your observation. X bar is the sample mean. And sigma was your standard deviation. So I'll give you a good example. I guess we'll do this maybe for one of my kids. I'll do it for my daughter, Madeline. So, you know, we take her to the doctor's appointments and they measure her height and her weight to make sure, you know, how does she compare with other kids her age, right? Is she, a chubby baby or not eating enough food, or is she gonna be really tall for her age or whatnot, right? So let's say for 18, because my daughter's almost 18 months old, for 18-month-old toddlers, let's say the mean weight is 20 pounds. I don't know. I could be, so let's say 25 pounds. I actually should know this. I don't, but let's say it's 25 pounds. I can still carry her. I'm not terribly strong, so let's say 25 pounds. So and then let's say the standard deviation is maybe 3 pounds. Well, let's say my daughter weighs 31 pounds. Okay, so my daughter's kind of heavy. 31 minus 25 divided by 3. So that means my daughter Madeline would be 2 standard deviations. Her z-score is 2, which means she's 2 standard deviations above the mean. So she's at a very high percentile. If you go back to the normal plot, that means that she's right over here. So if 95% of data is in between 2 standard deviations, so if I kind of chop that up by half, 47.5%, another 47.5%. So that means that she's in the top 2.5%. So sometimes, like, when you go to a doctor, they'll say, oh, your daughter or your son, whatever, is in the top 2% for weight for their age or height for their age. And they're basing this on a bunch of medical data that doctors kind of collect from a bunch of patients. We belong to Kaiser, so I don't know. Maybe they're using Kaiser data. Maybe there's a national register database for, what heights or weights should be for kids of a certain age. I don't know. But, just remember that's how we calculate a z-score. So z-score is a way to kind of provide a metric for how many standard deviations are above or below the mean. We use that z-score in the confidence interval. So when you have a 95% confidence interval, just so you know, when you have a 95% confidence interval, usually what's going to happen is that you want 95% of data to be captured. So you're going to be going with a z-score that's representing 95% of the normal distribution. In fact, I believe the z-score is 1.96 for 95% CI. And you can actually calculate that, and I'll show you guys a calculator when we do some practice tomorrow. You may want your graphing calculator handy. There's also tables you can look up on the internet too that can tell you what z-score to use. There is actually a feature here, but I'm not going to do a calculator demo today. I'll do it tomorrow. But let me just talk about what happens. So yeah. So determine the portions. If you need your confidence will cover. Actually, you know what? Let me let's hold off and go, because I think we actually need to actually get the calculators out and do this. So we'll hold off on that for now. But let's go over here. So the margin of error is this. So you take your sample mean x bar and do plus or minus z times sigma root n. So for example, Joe Biden was expected to get 50% of the vote. We're saying plus or minus 4%. So the 50% would be the x bar. The 4% would be all this right here. Where the sigma is a standard deviation that we probably know about the population and the number of people we sampled, and then z-score. So when the confidence level gets smaller, the z-score also gets smaller. So for a high confidence interval, you're going to have a high z-score because you're trying to capture more of the data, right? That's what's happening there. Now, of course, if your standard deviation is very small, it means you're not seeing much variation in the data. That's also going to have a very narrow confidence interval. Or if your n is really large, as you can imagine, if you sample more people, the more accurate your answer is going to be. So then you're able to also narrow the confidence interval as well if you sample more and more. But if you only sample maybe a few people, that's not going to really lead to a very small confidence interval. It's going to be very big because you're not really sure if you're capturing the true mean. If you only survey maybe 10 or 20 people, if you survey 1,000 or 10,000 people, that's going to result in a smaller margin of error, right? So also think of it this way: larger sample size more accuracy. That's also kind of, hopefully that makes some sense there. So there's some trade-offs. So I was correct. 95% confidence interval 1.96, and 90% confidence interval the z-score. So these are z-scores, just so you know. This is z. This is z. This is z. This is z. The 2.1, just so you know, represents sigma over root n. So whatever our standard deviation is divided by the square root of our population size. And you can see here for 95% confidence interval, that's pretty wide. When you lower the confidence, so yes, you are more accurate when you make a narrower interval, but you're not going to have as much confidence because you might miss but what if the population mean was 267.9 and then you're saying 268.5? Now you've missed the population mean. So that's a trade-off there. And just so you know, it's only going to cover the errors in sampling. So that's what, like for example, maybe you didn't quite capture the true proportion of ethnicity in your sample compared to the population, or the true age distribution of your population. So it really is just explaining errors in your sampling methods really more than anything else. Notice source of variation of bias in the sample influence. Yeah, you're assuming that nothing else is influencing your data, assuming you're doing things randomly. And there are practical difficulties such as undercoverage, meaning maybe you didn't ask enough people, or maybe you didn't make sure you try to capture all the different categories of ethnicity or socioeconomic groups. Some people may not respond to your survey, and maybe if they had responded to it, that would have swayed the result in a different direction. So sometimes you have to wonder about that too. But the thing is that those things are not considered in the margin of error that you do. So you have to be mindful about that as well. And again, margin of error is this, z times sigma over root n. If you wanted to solve for, say, n, so say, so Joe Biden's margin of error was 4%, right? So it'll be 0.04 actually. And say you had 95% confidence interval, so z is 1.96. And say the standard deviation was, I don't know, like 2. What I'll do is 0.02 because you're doing percentages. You want to figure out what n was, how many people were actually sampled. Well, this is where you need to get a calculator out. So I have a calculator right here. And algebraically, what you would do is you would say, okay, well, 0.04 equals 1.96 times 0.02. This is stuff we're going to work on tomorrow, just so you know. So you multiply both sides by root n. Then divide both sides by 0.04, so root n equals 1.96 times 0.02 divided by 0.04. So you get about 0.98. And then you got to square both sides. Actually, something seems a little off here. Hold on a sec. Actually, that's a really low sigma. Let's say the sigma is 2. I don't know, I'm just making up a number. Because otherwise, this just seems too small. Okay, so but when I redo that calculation, I get 392. And if I square both sides, hold on a sec. I'm really messing this up here. take 3. So times 2 divided by, I'm again being totally hypothetical. Sorry, I got 98. And if I square that, 9,604. So it means that I probably had 9,604 people in my sample. Again, you have to be told what the standard deviation is. You have to be told, hey, I'm doing 95% confidence interval, so use 1.96 for Z. And again, there's a way you can calculate the Z-score for various confidence intervals using the calculator, or you could look it up on the internet. And then say the margin of error is 4% or 0.04. So you could calculate that. And so you can see that, essentially what you do is you divide both sides by M, multiply both sides by root N, and square both sides. And that's how you can do the algebra for that. So let's try one more example here. And then of course we'll look at this. And then we'll kind of talk about what tomorrow will entail, and I'll show you some of the problem sets we'll work through. Okay, 1 sec here. Okay, sorry about that. So yes, let's take a look at this here. Suppose that we want to estimate the population mean scores using a 9% confidence interval, and we're instructed to do so such that the margin of error does not exceed 3 points. Okay, we call sigma equals 60. Okay, well, sigma 60. Okay, what sample size will be required to enable us to create such an interval? Okay, so let's look at the actual algebra that goes into this. So remember, sigma is 60, right? And if you want a Z-score confidence interval of 90%, means that Z is going to be 1.645. So you put that over here. And you don't want a margin of error that's more than 3. Okay, so plus or minus 3 from the sample mean. And so then you would need to survey at least 1,000 people. That's what it looks like. To ensure margin to not exceed 3 points. So sometimes you kind of go about a survey with that in mind, that, okay, maybe, you don't want your error to be that big, or there's a certain error that you are trying to strive for. Of course, if you want the error to be even lower, what if I actually want the error to only be 1? I don't want to be off more than 1 from the mean. Well, then if I calculate that, that's going to be even crazier. 1.645 times 60, if I square that. So now I got to survey even more people. So if I want even a tighter, a smaller margin of error, I have to survey more people to get that to happen. So hopefully that seems intuitive for that one. And you can't sample a fraction of an individual, so then you round up, like in this case, 1082. Or if I want a margin of error of 1, then it'd be 9742. So yeah, sorry, you do 1083 for this one. Okay, so that pretty much introduces what a confidence interval is about, giving a lot of the basics. Things can get pretty complex. This is some stuff from an AP Stats course that I sometimes borrow from Mr. Hahn. We'll probably go through this again tomorrow to kind of make sure that you guys are getting this. You can see the same schematic is used. It's a really popular schematic, so it seems. We'll kind of ask some qualitative stuff here about confidence intervals and whatnot. Looks like this is about Barack Obama, or in this case, losing weight. Constructing it, how to actually build it if you're given some information. So we're going to go through this stuff as well. And then I'll give you guys some homework from this that you guys will do Tuesday and Wednesday night, and that we'll discuss on Thursday. And then by then, hopefully you guys feel, again, pun intended, confident with confidence intervals. And then I could just do a take-home test that I could, same thing we did last time, maybe open up on Thursday afternoon, and then you guys can do it whenever you want over the weekend, but have it done by Monday. And I'll give you 2 attempts, just like we did before. But I'm going to kind of, really kind of contain it within everything that I've mentioned in this video, and a practice that we'll do tomorrow in class. And then on Thursday, excuse me, on Thursday, we'll definitely have a discussion about the project, what kind of project I have in mind. I have to carefully think this through and maybe do a little research. As you can tell, I didn't really do much research over spring break. I really just took a break because I think we all needed one from school. But I'll think of something that'll be kind of worthwhile, and that's something that you guys can easily do. It won't be as maybe as painstaking as the data collection that we had. That was actually very painstaking, but something that's going to be a little bit easier to do, but hopefully worthwhile and impactful for you guys. So I'll think of something and I'll do some research over the next couple of days. By Thursday, I'll tell you what this is. It's something, but similar where you got to write a paper, you got to do a presentation, you got to show me the work you do. And it'll be in groups again. And the presentations will be done for everybody on Zoom because, we're going to be on Zoom on the 20th. That'll be our last day. Anyway, there'll be other stuff here as well. So any questions at all? No? Okay. I think what I'll do is I'll go ahead and end class early for today. What I'd like you guys to do is, obviously enjoy today, but I'm going to put some other materials in there, and feel free to take a look at the materials. Or if you want to watch a video again. But we're going to pretty much hit the ground running tomorrow at 12 o'clock, where we're going to start doing some practice problems with confidence intervals, and then kind of maybe infuse a little more theory into it. And I think that should kind of essentially cover the topic that I really want to cover with you guys. So so I know it's a little early for today. So again, enjoy the rest of the afternoon. I'll put some materials in there in just a little bit. And yeah, I think that is it. Let me stop the recording.